Hello. Before we do anything, we're going to test this audio because I think I might want to actually try a little bit. Only a little bit. Hello. Before we do anything, we're going to test this audio. That sounds great. Sounds absolutely fabulous. Okay. So, um, official start, right. Let me think a little bit about what I'm going to say. All I needed was bullet points. You know what? Do I need bullet points if it was all just in my head? Okay. Oh, I need to plug this in. Okay. And the technical difficulties begin. Okay, we can do this. We can do this. Okay. If this doesn't work, no. Alright, we need to find the USB-C cord. Or what is? Longer than we need, but this will get the job done. Okay. One more time. Yes. Okay. Yeah, no. YOLO. Alright, gotta take this from you. Okay, silly little pants. Can't live with them, can't live without them. Okay. Alright. Today, we are closing this window. And we are actually starting in 3, 2, 1, 3, 4, 5. Okay, I now have a time limit. I now have 30 minutes to do this perfectly. Otherwise, I have to go into my cold garage. Get out of here. Okay, so official start. Hi, what's up, everybody? My name's Phil. Enough with the intro. We are talking about what is tensor multiplication. And to be honest, I don't know if it is previously a thing or what. Like, I did some browsing online and I saw like a Quora question about it. Where someone's like, you could do that, but why would you want to do that? I looked into what happens like when you try to matrix multiply tensors in PyTorch that have more than 2 dimensions, and there's a whole list here. And basically, I think the short answer is that basically tensors are broadcasted, and I haven't fully like grokked this, and I probably will after this, but disclosure that I haven't at the moment. So what I'm thinking about is how can we just define something that's more like a matrix multiplication for the general case of number of dimensions in your tensors. So let's start at the beginning. This is the last slide, but let's take it back to the beginning. So as you can see, my drawing skills on GoodNotes got better um, as I worked on this. So this was actually from I was just thinking about, like, just as a side note, I need to keep my eye on the time, but I was thinking, like, how do ops get counted? Like, at what level do ops get counted? Because it's like you could count it like this, like 1, 2, 3, 4. You could count it like whatever. Like, what happens with recalculated values for like your machine learning model? Like, when you're talking about operations on like a GPU, are you talking about like um, like assembly instructions, or are you talking about how many multiplies can I do or something? Like, how many divisions could I do or something, right? I don't know. Um, Excuse me. And like, I just don't think it's that obvious to normal people. I don't know. So let's walk through a matrix multiply. I'm sure this is like beating you over the head with a stick about this. But you know, at least it's like a warm up. So how this talk? Oh, okay, come on, dude. How I'm gonna like basically how I basically organized this was that this is gonna be really incremental. I'm going to sort of present like a warm up, something you might understand, and then I'm gonna like take it up one level, and we're gonna do that a couple times. So while this might be super redundant for you, redundant info, I take it to a point where it's like I can't find this online anymore. So like maybe this is what they talk about in like a next level abstract linear algebra class, but I don't see it. And then also, so a motivation for this is that when you have linear layers in neural networks, which is they're like in pretty much all of them. Like transformers have linear layers. You basically have linear layers, the attention function on the output of those linear layers, and then you have linear layers. So these linear layers are everywhere. And in those linear layers, uh, the main thing is a matrix multiplication followed by an activation function. So that's why we call the output of linear layers activations. Um, so the thing is, when this, I think this most struck me when reading the Vision Transformers paper, as someone interested in perception, was that everything gets flattened so that it fits into linear layers. Um, yeah, but when you have, I need to hurry up. So, but let me just get to this motivation. So when you have like one image frame, that is inherently a three-dimensional tensor, where you could then consider every value being one value on a number line. Um, so because of that inherent 3D structure in, say, an image frame, why do we get rid of that relationship between the values by flattening it and then just like putting it into a linear layer which does just a regular matrix multiplication on it? Why couldn't we just do a tensor multiplication that I'm about to explain? So I think like there's absolutely no way that I could be the first person that thought about this. Um, but and like I hope that I will make the time to run some experiments with replacing flattened tensors put into linear layers just with a tensor multiplication, a linear layer using tensor multiplication instead of matrix multiplication. Um, and then I know what you're thinking. I know you're thinking like, oh, this is just gonna be like a batched matrix multiplication or something like that. And I'm pretty sure you're wrong and that it's different. And if I'm wrong, I'll admit I'm wrong. I always do that. Like a good engineer scientist guy. So let's get into it. First, we're gonna just walk through matrix multiplication. So simple that my nephew could understand. So simple that a middle schooler could understand. So if you know, if you know a middle schooler, if you have a middle schooler, maybe, and you know they can pay attention in a math class. Maybe you should grab them because maybe they would understand this too. So matrix multiplication. So a matrix multiplication takes in two matrices and outputs another matrix. So the dimensions of the first one, let's say it's m by k, so m rows, k columns. The matching shape has to have the matrix you multiply it by has to have k rows. The columns of your left matrix have to match the rows of your right matrix. And sorry, just to clarify, we're multiplying this matrix by this matrix, and the output is going into this matrix. So the reason why, and so this is the confusing thing about this talk, that if you don't understand now, you will guarantee to be lost for the rest of it. So you might as well just turn on your focus to the max right now so that your chances of getting lost later go down. So the reason why these have to match is because this output matrix is going to be resulting in m rows and n columns. And that's why it's drawn like this, so that the rows match up with the rows and the columns match up with the columns. And this is just this is just so much better of a way to visualize it than I was taught in school. And even when I first learned about matrix multiplication, I was probably like, I don't know, like maybe I first saw a matrix in middle school. No, I first saw a matrix in elementary school. I definitely did some matrix addition and maybe scalar multiplication in middle school. And I'm not sure if I remember doing matrix multiplication until junior year of high school. It was always just a little oh yeah, don't forget matrices are super important in high level engineering. Yeah, but my point was that it was always drawn here's one matrix times this matrix equals this matrix. You just had to keep track of the row and the column, and eventually you got it down just by the muscle memory of remembering. But this is just so much easier way to draw it, and that actually builds the intuition for how we could even reason about tensor multiplication. So the result of these two vectors that go into this, the result that goes into this space is the dot product between these two vectors. And I know this is obvious for some of you, but bear with me. Or just skip ahead 10 minutes. So the result that goes here is the component-wise multiplication and the sum of that component-wise multiplication. So what goes here is 1 times 17 plus 2 times 21. This result is what goes here. And I was just counting ops when I first drew this a while ago. The rest is new slides. So get it, got it, good. Okay. So now, where is matrix multiplication happening in a linear layer? So this is how we often see neural networks drawn. And we're going to disregard the bias, the scalar bias, which is one more weight. I guess it's one more vector. But added to everything. But we're going to disregard the bias. And you have an input vector. And so for an output node, what it is what we just described. It's the dot product between this vector and this vector. So like this first circle represents this first location, and then these represent the weights. And by the way, like to just like bridge to make sure you're understanding, these are what we mean when we say parameters, like a 1 billion parameter model. These weights and sometimes biases, I guess modern ones might not use bias, but these weights and biases are the parameters. So now we have parameters in the sense of like, so parameters means three things to us now as good mathematician engineers. It means the inputs to any math function, the inputs to any coding function, and now specifically weights and biases. And then if you're in the machine learning paradigm over here, um, parameters, um, hyperparameters is any other parameters. So like in a math function, everything's parameters. In machine learning, the parameters are the weights and biases, and the hyperparameters are everything else. Learning rate, number of heads, anything. Maybe even like some might even consider like a function as a hyperparameter of a machine learning model. Everything else is hyperparameters. So just some vocab for you. Um, and then in the standard notation for a two parameter, like a two matrix parameter, as in like B and A is in this matrix multiplication. Um, the matching dimension, that K, is the inner dimension. So here 4 matches 4, and then the result is, you know, those dimensions without the matching inner dimension. Okay, so now I just want to like go over what I'm pretty sure batch matmul is, and it's totally fine if I get this wrong. I can be corrected, but here's a regular linear layer, and here's the matrix multiplication way we drew it if we're going to do this out by hand. And then here's batch matrix multiplication. So like you could think of it like this if you want to, that you have like say you put in one token vector and then you multiplied it by the weights to get your like the thing right before the activation. You have this matmul, and then you have this is the output, and then you would apply the activation to this. So the thing is, we could easily do that. We could do many token vectors at once by just having a stack of vectors, by having a batch of tensors. So when you do this computation, the thing is, so as we know, since we have three rows in A now, we're gonna have 3 rows in our output. So that's nice. So this is the same output as this first line. And this B matrix is the same matrix. So if you want, you could think of like 3 of these planes of weights going from this first vector to this output vector, this first vector to this output vector. So as you can see, it's transposed between here and here, but anyways. So yeah, so, and this sort of goes into my motivation I talked about earlier. Then how would, like, so, I forget if I made these slides for batch or tensor multiplication, but if we tuck that over to the side, give us some more screen real estate. What if we wanted to consider a matrix as an input to a linear layer? Well, we could add some depth to all of these things. So now we could think of this as an input matrix into this tensor multiplication, and it will, if we just follow the same laws from the 2D case, then we can get a 3D output. So well, let's do it, right? Right? So as we can see, we can, so they still need to match on K, like in the previous example, but also notice that they need to match on this K1 too, because the output dimension needs to match this K1, and then this is that inner dimension that went away. And now when we look back at our neural network diagram, before in the batched case, it was the same B matrix weights, the same matrix, just like copied through here. But now, now we can actually think of these as fully, no, they're not fully connected. No. I'm not sure. Anyways, there are 40, yeah, it's definitely not fully connected, but there's 48 weights because in this B tensor, you have 3 times 4 times 4. So there's 48 weights. So at this point, the way we draw neural networks sometimes is not so useful anymore. But this is actually going to be pretty useful for us to explain the rest of this. I think I have 20 minutes left. Okay, so let's look at just this vector of the A tensor. And let's call the values A0, A1, A2, and A3. And then let's look at these values of the B tensor, B0, B1, B2, B3. So that box, this purple box, is, like we said, it's going to be the dot product between these vectors. So to me, looking at this screen, isn't something just begging to be done? Like begging to be tried? Is it just me? Okay, so, all right, let's zoom out a little bit. Maybe if I was presenting this live, I would take some questions right now while this marinates. But zoom out a bit, and here we are talking about tensor multiplications. Each tensor has 3 dimensions, and there are 2 tensor parameters. There's tensor A and there's tensor B. What if we added, what if we renamed the output tensor to out, and then we added tensor C that follows the same properties as A and B? All right. So as we see, we still need that inner dimension K0 to match the length of these so that we can properly do some type of dot product between these vectors. And then we also notice that these B and C need to match on K2. They don't necessarily need to match on K1. And then sort of circling back, we realize that circling back, we realize that that third dimension of A doesn't have to match this third dimension of B. This just happens to be 3 by 3, but it doesn't necessarily have to match. Now I wish I tried to make them small numbers to make it drawable, but now I'm a little upset I didn't make one of these like 5. But anyways, K3 and K1 do not have to match, but these K3, these edges all do have to match. So now we're at a point where we realize that all of the dimensions of all our tensors can be written as these Ks. So we see in tensor A, the size of it, like the shape of it, whatever you want to call it, it's going to be, and we're following that the first is the rows, the second is the column, so naturally the third is the z-axis. So we have K0, K2, I messed this up. Actually, if we wanted the rows, we'd have K2 first. It doesn't matter, but if we wanted the row to follow convention, we'd have the rows first. K3, sorry. Then we would have K0, the columns, and then we would have K1. For B, we would have K0, K2, and then K1. And then for C, we would have at least I consistently got it wrong. K3 rows, K2 columns, and a depth of K0. And these obviously all these colors match. Okay, so, and then the output tensor is like in the matrix multiplication case, that it's the last dimensions without that matching dimension that they all share. Okay? You picking up what I'm putting down? They all share K0, this purple line, and the output tensor is all the other dimensions. It all just lines up perfectly like that. It's cool, right? Okay, so this formula we tucked away in the side, let's bring it back and let's expand it now that we're adding C. But first, let's acknowledge that the original matrix multiplication is a special case of this tensor multiplication that we're defining, where every term is multiplied by 1, and we could think of this C tensor as being filled with 1s. Yeah. So, but if we put other whatever values into these, like say we had, and let's just to keep the notation simple for now, we could obviously imagine filling out the rest of these. But for this one entry, this one box, if we label this vector as C0 through C3, let me zoom in because I actually don't know how big it looks for you. So we label just this vector because we're calculating this purple box. Then the equation for that is we replace these 1s with whatever we put in the boxes. So for this spot, we do something like the dot product, but it takes in 3 parameters in this case, 3 vectors in this case. Yeah, so component-wise multiplication, the sum of all of that. That's that box. Okay, another time to sit, maybe pause and marinate, and if I was like presenting this, maybe take some clarifying questions or anything about anything I talked about so far, because I don't want to get like really off topic. I'm like imagining. But so yeah, so hopefully this all makes perfect sense so far. So the way we stepped up like the difficulty last time was we drew first. First we drew the C tensor, then we looked at the equation for one of these. Let's instead start on the math side for a sec, and then to take a step up. And let's say, like, what if we added another value, right? What if we had a D tensor, and this is one vector from the D tensor, and it's somehow orthogonally pointing at our output matrix, but we can't draw a fourth axis. We already used forced perspective to let us draw 3 axes, but we can't draw the 4th axis. So first of all, we want to like make a general form for this eventually, right? So let's aim to sort of get this into this form where we can just call everything x's. And just in case you haven't seen this notation, This is big pi, big bold pi. Maybe it probably has a name I can't remember right now. But this is just the product across all j's. So it's the product of all of these, and then it's the sum of all of these. So it's exactly what we've been doing this whole time. Just big pi is not like 3.14, 3, etc. It's the product of all of these. So to do that, we're gonna rewrite this equation right here, just so everything can be an x, so it fits nicely into this, and maybe that'll help write code too. And please, someone who has looked at equations like these more often than like looking at code. So I color coded like these sub things just to show that like these values all correspond to things above and below. So anything that was an A now has 0 as its I index. And then anything in J, J goes from 0 to K sub 0, as you can see here. It's the thing, the axis that the inner dimension that matches has to go on. Okay. So now it's pretty simple to see that for that one box we just needed this. Oh, and so this equals this. I guess I forgot to put the equal sign here for that one box. Okay, now to get all the scalar boxes, I guess this should have an index too in I don't know if you want to be formal. There's just some pseudocode, but parallelized somehow basically is, you can imagine it in two ways. You could imagine sliding this box across every single one of these boxes, in which case that would be like a for loop. Or somehow parallelized, you could imagine just all of these things happening at the same time. Okay, so just pause here for a second. If anything's unclear, let's see. I think this is pretty clear. So like at each iteration of this for loop, you're on like a new, like say you incremented K2, you started on this K2 and then you're on this K2 for all of these, all of these, all of these, all of these. I'll just point to one more. If you incremented K1, the first K1, I don't really know which direction these are going in, but say this was your first K1, then you're working with like this plane. Is that right? No. You're working with like this row. It'll be this plane, like this frontmost plane, of course, and then like taking depth steps. This can get confusing pretty easily, honestly. So thank God for colors. Okay, so we have one more wall to break, and that is this D situation. We didn't draw the D tensor. How are we going to point that D tensor at this output so that we could calculate it nicely like we have with this? So here's how. Here's one way to visualize it, because I don't know how else you would in like following this format, is that consider that originally the same way, like we sort of had that hidden C tensor where it's filled with ones, and it's basically like an identity tensor where this is the same as this thing with its tensor multiplication, also including this c. Then we sort of have this extra dimension, like k4, where k4 is 1. And this is just everything in that one dimension. Now, say we had k2, then this is just, like, you could just draw it as a copy, is what I'm saying. As many copies of the original one as you needed to have as many dimensions as you want. And one sort of issue here we have is that dimension means a couple things, because does it even? I don't know. You have, but anyways, you have these as your dimensions, and this is going to be your resulting output tensor's dimension. So this output tensor on the left, how do we get that big? This output tensor is part of this output tensor. It's just that this is when k equals, if the k's go from 1 to 0, I mean, if the k's start at 1, this is damn it. All right, this is the size of this dimension. So I messed this up a little bit, but I think it should make sense. Is that you have these are part of the same tensor. This is just some way to visualize it, so that you have, like, you know, what occurs on these axes. If that made sense. So this is it. You could do this as many times as you wanted to add as many dimensions as you want. And circling back, you could, like, what I would love to see is experiments where in any neural networks where a tensor is flattened and then put into a linear layer, to use this instead. And now, what other things that are kind of like this, that are popular at least? There is convolution 3D, for example, but that's typically convolution 3D. I wonder if I could pull up a visualization or something. But that's like you have an input tensor, and then you have a smaller tensor, and then you slide that / put it on every place it fits on the input vector, and then you have a result where everywhere it fits, it was that tensor multiplication. But that's not even quite right, actually, because when you do that, I'm now sort of just like thinking out loud. But when you do that, that's like, could draw it, but anyways, I think I'm running low on time. But it's not convolution, or maybe it is in the like mathematical definition of convolution that I like never really learned or something. Like one time I started looking into it, and then it was like looking like it had to do with more with like probability. And I'm sure it can be used in probability, but I think the way I know convolution being taught it through like a formal like master's in AI setting was like in the sense of just like the math operations. So like how most people I think of convolution, but it's not convolution. It's not batch map mul. It's tensor multiplication. Yeah. So that's what I want to see, is experimentation with that. And now, so everything I said so far or everything I said before, like talking about experimentation, whether it would work better, like perform better on like evaluation data sets. This is all like solid, like this works. Like you could get these resulting tensors. Um, whether or not we know whether it would be useful or not. But now let me talk about completely theorizing, completely pulling this out of my, like, why maybe this could be a place that we can explore now. And so one thing is that we have, um, I think something obvious is that this would probably run pretty slow, especially this naive implementation where these are actually just normal for loops, and this isn't actually happening on the same clock cycles. Um, but we're at a point where our VRAM budgets are getting so high, our parallelization techniques are getting a lot of eyes on them, so really thought out. That what if this could work? Like, what if? And let me also clarify what. Let me find a nice one with just the three matrices. This one, I think. Sure. To be clear, I've been thinking about this like in the beginning. A is like your data, your input, your x's. B is your weights. So your weights times your data. Like these, B is the tunable thing. B is the tunable thing. A is your input, and then we added C. Um, C is how I've been visioning it. People could, draw this up, like architect this out however they want. But I've been thinking about C also as an input. Um, so like A and C are inputs. So this could be, I think, like relatively unexplored way to do sensor fusion, to do multimodality, to do this type of thing. Because what you have when you're training a neural network is that you have something like this over and over again. You have several layers of this type of thing. So it's like this activation on this thing, and then this goes in as the input to the next layer, and then you do your matrix multiply, and then activation on this thing, something like that. So I've been thinking of like A and C are different modalities, and then these parameters, the way that they're tuned is that you go through a neural network how you typically do. You have the target Y, you define some loss, some difference between what you expect to get in your training data and then what your model produced. And then you do back propagation, you find the partial derivatives of like first you do it for the second to last the last layer, but this is also the result of a function. So you do the chain rule, and then you find those derivatives for what influenced this, and then you do that all the way backwards through the network. So one of these things, so let's like clear our mind and then think of this as like one layer, just like one tensor multiplication. Oh no. So this B is, this cell is a result from A, B, and C. So it's like, yeah. And that's all.